All right, so here we have a Khan Academy problem. It says a satellite of mass m orbits Earth at a radius r and speed v naught as shown below. An aerospace engineer decides to launch a second satellite that has half the mass into the same orbit. So the idea is we're going to put another object in the exact same path of orbit that this current object has. So the question is, what is the speed v of the lighter satellite? So the real question is, does reducing the mass change the velocity? All right. So you might think intuitively, well, if I reduce the mass, maybe it'll go faster. But let's actually try to figure out what's going on. So here we have the Earth, right? And then we have this orbit. Well, it turns out that all objects, no matter how big they are, how massive they are, if they have the same radius of orbit, right? There's our R value. If they have the same radius of orbit, they actually travel at the same speed, independent of their mass. And let's try to figure out why. So what we're going to do is draw a free body diagram of one of those objects as it travels around the Earth. Now, whenever an object travels in a circular path, okay, its velocity can be used to figure out its acceleration. So when it's in orbit, it's traveling at a constant speed. So its tangential velocity is actually a constant. But its direction is constantly changing, and that's why it's accelerating, because acceleration is a vector and has both magnitude and direction. So even though the magnitude of the velocity is not changing, right, it's moving at a constant speed, its direction is constantly changing. And the direction that it's accelerating in is actually inwards towards the center of the circle. So at any specific time, its acceleration is inwards. And its acceleration can be found by the formula tangential velocity squared divided by r, where r is, the distance to the center of the object. Don't forget, this Earth is right here. R is measured from the center of the Earth to the path of orbit, okay, to the object. So if we model the forces on the object that's orbiting, there are no contact forces. The only force on that object is the gravitational force of the Earth, right? Which is equal to gmm over r squared, big M being the mass of the Earth, and little m being mass of the satellite. So if we apply Newton's second law, saying the sum of the forces is equal to the mass of the object times the acceleration of the object, and we replace the net force with gmm over r squared, because that is the only force acting on the orbiting satellite, and we replace a with v squared over r, right? We can actually simplify this relationship. We'll divide each side of the equation by m, okay, and we multiply each side of the equation by r, and we're left with v squared equals gm over r squared. And if we take the square root of each side, we say that the velocity of that orbiting, sorry, I made a mistake here. The velocity of that orbiting object is based on three things. G, the gravitational constant, capital M, which is the mass of the Earth, right? We can add a little e in this case. It's not always the mass of the Earth, but the object that you're orbiting. And then R is the radius of orbit. So what this tells us, what this equation tells us right here, is the mass of the satellite doesn't matter, right? It's not in the equation. It's inconsequential. So the velocity does not depend on the mass of the satellite. So even though you are launching a lighter satellite, it says it's half the mass does not factor into the velocity. So in this case, the velocities will be the same.